Good evening, everyone. Thank you for being here. This public lecture is part of the long-running sequence in the Oxford Symposium of Quantum Materials. And the leader of that initiative here today is Professor Amalia Cordia, who's sitting there. So this year, the symposium is focused on frontiers of quantum microscopy, which is the challenge of visualizing quantum mechanics at the atomic scale. It happens that many, if not most, of the world experts on quantum microscopy are sitting here in the audience with you. So for me, it's a great pleasure to be here to see all my colleagues in that regard. So our public lecturer tonight is Professor Stephen Blundell. Now, one is no longer supposed to say that someone is a Renaissance man because that's gender specific. So instead, I would say that Professor Blundell is a Renaissance person. And his work and his achievements span an extraordinary range. Certainly, I wouldn't have enough time to cover it here. But first and foremost, his own research has to do with using high energy physics, elementary particles, muons, which are then injected into modern quantum materials, the materials that many of us study by imaging techniques, to understand what's happening inside at the atomic scale. And in terms of the range of energies that he actually needs to use for his research, it's one of the widest that you can imagine in physics. It's really extraordinary. He's a distinguished world leader in that field. And for example, last year, he was awarded the Bragg Medal and Prize for using muons to study quantum matter. But that's not all. He's also a distinguished author. He has authored many textbooks on physics. Too many for me to have read. I have read some of them, but not all. And the most, many are about magnetism, superconductivity, things that quantum materials people love. But the most recent one is about general relativity. And so that's an extraordinarily wide range of knowledge, from superconductivity to general relativity. And these books are beautifully clear. In fact, they're so clear that when you read them, you learn that you don't understand what you thought you understood. But anyway, they're wonderful, they're fantastic. And then furthermore, just speaking now personally, I relatively recently moved to Oxford and had the privilege of beginning to collaborate with Professor Blundell. And effectively, I've been under his tutelage. A somewhat aged student, you may think. But I've learned a tremendous amount from him about modern non-conducting, spin-active quantum systems. And it has reoriented the focus of my own research. So I'm tremendously grateful to him for that opportunity. Okay, so without further ado, I'd like you to welcome Professor Steve Blundell to give us this evening's lecture. Thank you.
Well, thank you, Seamus, for those very generous words. It's a lot to live up to now after that introduction. But this quantum materials public lecture this year, as Seamus explained, is following on from this conference we've been having here in Oxford on seeing the quantum nanoworld. And we've today heard a large number of talks on the latest breakthroughs in that area. Many of them have been actually made through innovations that Seamus himself has pioneered and done. But what I'm going to try and do this evening is to talk about this quest and put it into a bit of context of what it means to see the quantum nanoworld and why that might be surprising. Well, why the nanoworld? Well, the nanoworld is where atoms live, and atoms are on a very, very small scale. They're on the scale of nanometer or sub-nanometer. That's what you have to see down to see atoms. So 1 nanometer is a billionth of a meter, a millionth of a millimeter. So it's a very small distance. Now, in fact, the notion of atoms, the fact that atoms might even exist, it's historically speaking quite a recent idea that's been confirmed, although, as I'll try and explain, it's been hanging around for a long time. And so atoms have this rather long and controversial history that I'm going to say a little bit about, and then maybe just to show what an achievement it is that we can actually now see atoms, talk about them, worry about where they sit, where they exist, and how they might interact with each other. Well, the idea goes back a long way. You could go back to, the date is questioned by scholars, but let's say the 5th century BC. In the book of Genesis in the Bible, it talks about us all being formed from dust. For dust you are, and to dust you will return. What is dust? Well, it's tiny stuff. We're made of tiny stuff. Democritus in the Greek world was pioneering a similar idea. He used the word atom, something that was uncuttable. And he felt that the first principles of the universe, as he said, are the atoms and the space between the atoms. And the space between the atoms is called the void. So everything else, he said, it's just in your mind. It's thought to exist. But what actually is there are atoms. Atoms are unlimited in size and number. They move around the whole universe. And essentially that generates everything, generates all composite things. What are those composite things? Well, fire, water, and earth and air, the 4 elements, as they thought. All of those things are just, what are they? They're just aggregates of atoms. And Democritus himself was a student of somebody else who was possibly the pioneer of atomic thinking, although whether he existed or not is, I think, debated. Democritus was really somebody who was dedicated to thinking about what are the fundamental principles of the world, and he thought they were atoms. So the net result of this, I guess you could ask this question, what is the world ultimately made of? If you were to magnify everything up, is it just a continuum like a jelly, an undifferentiated blob all the way down, or is it made up of individual bits? And of course, the Greeks were arguing about this and they couldn't really know. There were different viewpoints on different sides, but there wasn't really a way of settling the matter. So different people had different views. And I guess one of the problems, as we're going to see, is that the atomists, people like Democritus, they kind of backed the wrong horse philosophically because they were not the ones who won out. So let's just say a little bit about what this idea of the atoms and the void is. Atoms are these elemental corpuscles of matter. That's how they thought. They also thought that maybe the way they collide, the way they interact, was generating all of the additional properties. They also thought they had particular shapes and maybe sharp bits on the end. So the reason, something might taste bitter is because you're tasting the sharp edges of atoms. But then, of course, if you have a notion of atoms, you also have a notion of the stuff in between the atoms, the so-called void, the region that separates the atoms. And that was a bit of a logical problem for some people, because if you have a nothing, the void is basically nothing. Well, does that exist? I mean, nothing doesn't exist, in which case the void doesn't exist, in which case the idea of atoms is ludicrous. And that was one of the arguments that was used by some philosophers and unfortunately carried the day. So this was the problem. A theory of matter is also a theory of the absence of matter. If you're going to have atoms, you've got to have the stuff that's around those atoms, and that caused a problem. I think another problem as well is the company that the atomists kept. So many of Democritus' ideas were taken up in a later century by Epicurus, who founded a school that was based on atoms, but he then combined it with a whole lot of other particular ideas, one of which was particularly that the way to be happy in life, and that's what a lot of the Greek philosophers spent their time trying to understand, was essentially mind your own business. So, don't worry about God, don't worry about death. If there's stuff that's easy to get it. What's terrible, just endure it. So basically, as he said, the gods exist in a state of bliss. They're unconcerned about us. And so Epicurus said, well, he didn't mind competing with Zeus for happiness as long as he had some food and water. So that was basically his philosophy of life. So the Epicureans had that philosophy of living well, but it was coupled with atomism. So these two ideas bizarrely got linked. And so if you didn't really like the other bits of this philosophy, which the early Christians didn't, then Epicureanism and hence atomism was a bad thing. But several centuries later, and this is now into the Roman era, Lucretius wrote an amazing poem called On the Nature of Things. He wrote it in this Latin hexameter, and he speaks incredibly poetically about atomic theory. It's probably the best resource we have because it's so well preserved. We've got very little left from Democritus. And he points out, when he's talking about atoms, he says, you know, these atoms, they have to be somehow differ in their particular properties. We, of course, would think about different chemical elements. So what seems to us the hardened and condensed must be of atoms amongst themselves more hooked, be held compacted deep within, as 'twere by branch-like atoms, of which the chiefs are diamond stones. This is part of a long passage where he goes through all the different types of materials and say, well, it must be to do with the different ways they're made up, different shaped atoms. But as I said, this atomic theory got, unfortunately, they backed the wrong horse because the great philosopher of the ancient world was Aristotle, and he thought this was all nonsense, partly because he didn't like the idea of the void and nothingness, but for various other reasons. And so the idea that everything might consist of atoms was therefore relegated to the dustbin of history for a long time. We're in Oxford, so I have to mention Robert Grosseteste, who was a Bishop of Lincoln, but was also spent a lot of his career in Oxford. And he has this wonderful passage where he talks about atoms. He thinks of them as, again, specks of dust. I guess this is going back to Genesis. But when you see dust illuminated in the morning sunlight, you get a sense that the world is made up of tiny little bits. And he said, you know, behold how reason can see in an atom the infinite power, the infinite wisdom, the infinite goodness of the Creator. And to see this is to see the creative Trinity in such a way, therefore, as if from one mirror, from each one creature, many similitudes of the creative Trinity result. So again, it's a wonderful meditation on the nature of things making up the world we live in and how this is, in some sense, not something that should be associated with Epicurean philosophy, but something that's actually can be incorporated into the Christian world. But still, all the way through the Middle Ages, atomism was not very popular. And I think you have to get right up into a more modern period, into the 17th century, when you start to have people like Pascal and particularly Robert Boyle, again, somebody from Oxford. His laboratories were just on the high street here. And they were thinking about gases in chambers and where pressure comes from, and developing models in which the pressure of the gas is to do with the individual particles, the individual atoms, as we would call them, or molecules, bouncing off the edges of the container, and that's where pressure comes from. So they were trying to understand what pressure is, and they were coming up with an atomic model for explaining it and getting quantitative predictions. And I guess another very, very important person in this respect, another person trained in Oxford, is Robert Hooke. We don't have a portrait of him, I'm afraid, so I've had to use a modern reconstruction that was done more recently because all the portraits of Robert Hooke were destroyed. But Robert Hooke was thinking a lot about these kinds of problems. He was thinking, Robert Hooke worked on absolutely everything. He worked on the weather, he worked on pressurizing gases, he worked on doing all kinds of different experiments, and interested in optics, electromagnetism, the whole thing, just an extraordinary individual. He'd started off, one of his first sort of scientific jobs was working as Robert Boyle's assistant. And one of the big ideas that Robert Boyle had, Boyle's law, was about compressing gases. And one of the phrases they used was the spring of air. That's a phrase we don't use very much now. But the idea that when you compress a gas, it bounces back. It has a spring-like quality. And of course, Robert Hooke is the one who came up with Hooke's law about stretching springs. So he was thinking all about this. And therefore, he very much thought about a world in which vibrations, the vibrations on a spring, were probably quite fundamental. And therefore, there were vibrations everywhere. And as we'll see later, his idea that light is a wave became rather important. It was all part of this springiness of everything. But he had some very interesting points about this. And I think actually his comments that he makes in the introduction to his book about the microscope, which I'm going to come on to for obvious reasons in this lecture. But if you read the preface of this, he makes a very important case about, I think, science in general and the questions of atoms in particular. because everybody up until this point had been arguing about whether the world was a continuum, a jelly, or whether it was made up of little bits. But to be honest, they were just talking about what view they preferred. And Robert Hooke thought the crucial thing you needed to do was to find a determinative experiment. So he said, all of the uncertainty and mistakes of human actions, essentially they come from a whole range of different things, one of which is the narrow, as he puts it, the narrowness and wandering of our senses. The problem is we can't tell whether atoms are there because they're too small, and that's because our eyesight isn't good enough. So if we're going to make any progress here, we need to find ways of improving our senses. So that's the first thing. But then he also has, he very much understands how human rationality can be deceived. So he talks about here, the delusion of our memory, the confinement or rashness of our understanding. It's no wonder that, our power over natural causes has been moving so slowly, that progress has been so slow. Even the forces of our own minds conspire to betray us. So he could see actually lots of scientists, lots of natural philosophers, as they would have been called, thinking of all this stuff and essentially becoming deluded. So, what's the solution? The first thing he says to be undertaken in this weighty work is a watchfulness over the failings and an enlargement of the dominion of the senses. In other words, if we're going to make any progress, what we need to do is build better instruments to study the natural world. So in other words, adding these artificial organs, as he says, to our natural ones, this is the crucial thing. By the invention of optical glasses, he says, for example, the telescopes that had just been invented, there's nothing so far distant that may be represented to our view. And by the help of microscopes, there's nothing so small as to escape our inquiry. So that's fantastic stuff. And he rounds it off. I've just taken a few extracts. He goes on for pages and pages. The truth is, the science of nature has already too long made only a work of the brain and the fancy. It's now high time that it should return to the plainness and soundness of observations with a capital O, on material and obvious things. So that's a wonderful sort of manifesto and a cri de coeur for the importance of experiments. And of course, he was to make good on that, so I'll explain in a moment. But just keeping this theme of atoms, the ideas were coming out that Robert Hooke never built a microscope that could see atoms. But evidence in the 18th century, and particularly at the turn of the 19th century, started to become overwhelming, and some of it came from chemistry. So in chemistry, when you have chemical reactions, you have to have certain masses of substances which will combine. And so you have chemical reactions, 2 lots of H2 plus O2 goes to 2H2O. And it was John Dalton, an English chemist, who came up with the idea that essentially this must be due to the fact that you're combining particles, as I'm showing in this diagram. And of course, that to us is all completely obvious, that this should be the way that it should be. So around 1803, John Dalton comes up with his atomic theory of chemistry, and essentially it's Democritus updated, but the reason he knows it's very likely to be true is because this is how chemical reactions work. So you have these different elements, the elements were being discovered, atoms can't be created or divided into smaller particles, they combine in these simple whole number ratios once you've sorted out what their individual masses are. So in a chemical reaction, atoms are separated, combined, or rearranged. So there we are. By 1803, the problem is essentially settled. Or is it? So this is rather late. This is Berthelot from the end of the 19th century asking, well, did anyone see a gas molecule or an atom? Now, chemical symbols, he said, can be dangerously seductive. The algebra of combinations, essentially what Dalton had done, is appealing. And of course, the human mind is naturally inclined to substitute for a direct conception of things, which is invariably lacking, a simpler view in terms of descriptive symbols that give the appearance of more completeness. So his view is that, this combining of chemical reactions in numbers, it's a useful shorthand. It's a nice way of calculating chemical reactions, but it doesn't correspond to reality. And he wasn't the only one. William Oswald, who did very important work in material science and various other things, he says, and again, we're talking very late here, he's writing this right at the end of the 19th century, atomism is a doctrine that has miserably failed in any serious attempt to explain through mechanism all known physical phenomena. It's even less likely to succeed in tackling the incomparably more complex phenomena of organic life. And so, of course, only a little bit later, we got the structure of DNA. But no, he didn't believe it. And Ostwald gave various scientists like Ludwig Boltzmann, who had developed statistical mechanics on the basis that there were atomic states, a really hard time. I also particularly like this one, Pierre Duhem, French chemist, writing in 1902, incredibly late. Upon noting that the ease and clarity with which all principles of modern chemistry fall into place in a treatment excluding the name and notion of atom, one cannot help but think that the unique success of the theory of atoms is an illusory victory without future. All things considered, modern chemistry does not support Epicurean doctrines. So there you are, hooking right back to the Greeks. Extraordinary, isn't it? So in 1902, and this is just 3 years before Einstein has his wonderful year explaining Brownian motion and all of the other things, already years after the discovery of the electron and various other things like the X-ray, atomism was still being fought. But of course, what didn't convince anybody is you couldn't see atoms. And that's the crucial thing. Is there a way of seeing atoms? So to do that, we have to wind back a little bit to the invention of the microscope. A number of people were developing this in the 17th century, but Hooke was one of the first. His microscope, or a model of it, is shown on the right of that diagram. It is extraordinary that this acts as a microscope. So what you can just about see here, it just looks like almost like a metal lock that's fallen off a hinge or something. But what you have in that little dot in the middle, I'm not sure my arrow is going to work. No, never mind. But there's in the bottom of that picture, you can see a little recess, a little circle. There's a tiny little lens in there. There is a thing that looks a bit like a compass, pair of compass pointy thing. You put your sample on the end of that. You use some screws to maneuver it right in front of the lens. Essentially, what this microscope is a tiny magnifying glass that you put your eye right next to, and then you have the sample right next to this. So you have to hold it right up to your eye. It's basically a magnifying glass. And but with this, he was able to see a whole new world. And he was then followed up, particularly in Britain, by Robert Hooke. And there were others as well. I'm not going to go through the complete history of microscopy. But Robert Hooke, starting here in Oxford, getting the idea particularly from Christopher Wren, his great friend, who pioneered lots of things but then lost interest and went off and did other things. Robert Hooke was a bit more persistent, took Christopher Wren's ideas very often, paying fulsome tribute to Christopher Wren's insight, but then taking it much further. And what Robert Hooke in particular did is he decided to work with a compound microscope. So rather than just having a single lens, he had two lenses in a tube. So his microscope, as drawn here, looks very much more like a modern microscope, or the sort of thing that you might have played with at school. So you can see a number of innovations here. First of all, there's two lenses, the eyepiece and an objective lens. Also, he realized that a very important thing you need to do was to illuminate your sample. So he's got here a candle, we'd probably use an LED light now, but anyway, a candle focused through a lens to produce a really good illumination of the sample. And he had something else which was absolutely crucial. Now, in a modern microscope, you might have photographic film or a CCD detector or something that reads straight into your computer. None of this existed in their time, so there were no photographs. So the question is, how could you get those images to show somebody else if they weren't there? And Robert Hooke was a fantastic draftsman. His pictures are amazing. So of all of those early microscopists, one of his great skills was he had this amazing printing system, which was his ability to draw. And his diagrams inside his book made it an absolute bestseller. So this is actually his drawing of his microscope kit, but then he would also do things like this. So this is one of the pictures he could see through his microscope, and this is his drawing of a fly, a giant, enormous fly. And of course, this is 17th century England, so everybody was also afflicted by fleas and bed bugs and all kinds of things like this. So this is what happens if you look at a fly and it's straight in front of you. So I hope, sorry, this is the flea. His beautiful drawing, and I hope you can just see the detail of the hairs on the side of the flea. So he'd just drawn this by hand through looking through the microscope lens. And sorry, I got ahead of myself here. Here's now a fly. So you can imagine looking down a lens and seeing this, seeing these eyes pointing towards you. Absolutely extraordinary. And of course, it's these extraordinary pictures that were then printed and distributed around caused Jonathan Swift to then go and write Gulliver's Travels about what happens if you have giant men or tiny people. All of this is inspired by these scientific developments. He was taking the mickey out of a lot of the scientists with some of their bizarre ideas as well. So some of it is a pastiche on the Royal Society. But yes, this extraordinary picture of a fly, I mean, just beautifully drawn. Here's one that looks a little bit more scientific, but actually it had technological implications here. These tiny crystals that he's drawing here are actually crystals from urine. So these are the tiny gallstones that can cause enormous problems and killed one of his friends, one of his Oxford friends. It was a common thing in the 17th century if you've got gallstones, no treatments for it. So, of course, he did experiments, I think, on his own urine. This is exactly the kind of person he was, but he was trying to understand, what causes this medical problem, and microscopy gave you an access to a world that you just didn't know about. So this book really just increased wonder, it increased understanding, hugely important. But as I mentioned, one of his other key ideas was this, the Hooke spring and the fact that everything was vibrating. And he saw throughout the natural world vibrations everywhere. And so for him, it was very natural when he asked questions about light to say that light was a vibration, light was a wave. And the other thing that he did was he came up with the inverse square law of gravity on somewhat specious reasons. He thought it was all to do with the fact that gravity was like some kind of energy wave, and therefore, as it went out, over a sphere of radius r, you're distributing all of that energy over r squared, so it would make sense that gravity would go down like 1 over r squared. And he mentioned this to Newton. But Hooke couldn't really sort of understand why the inverse square law would be so important. Newton worked it out. But Newton, being the kind of person, unlike Hooke, who wasn't willing to give any credit to his friends, when he wrote the Principia, he wrote Hooke out of the story and got very prickly when it was suggested to him that actually the idea of the inverse square law might have been suggested to him by somebody else. He was not the kind of person to ever give credit. So Isaac Newton also had another problem, which was that he was very clear that light wasn't a wave, that it was a particle. And he had very good reasons for thinking about that, because, of course, if you think about the way a light microscope works, light travels in straight lines. The very fact that you can see me and see the screen so clearly is because light travels in straight lines, and it's focused in the lens of your eye and projects an image on your retina, and that's what gives you the image. And if the light rays went all over the place, that wouldn't happen. So we're used to the idea of these light rays going in straight lines. And why might they do that? Because they're a stream of particles. That seems to be a very logical explanation. These particles, if they're not interacting, they'll just go in straight lines. They might bounce off mirrors. They might do something funny when they go through lenses, but it doesn't seem to be, they don't seem to be very wave-like. And the problem was, because Newton was such a successful scientist, he'd made such an impact, he became president of the Royal Society, and after Hooke's death, it's thought that possibly he was the one that was responsible for removing all of Hooke's portraits, which is why we don't have one left. That the idea of the wave theory of light got completely taken out of the equation. And it wasn't until many years that it started to be revived. So interestingly, one of the people who revived it was Fresnel, French physicist. He wrote an essay for a competition among academics in France, and he developed his wave theory of light and submitted it. And one of the people who read this, who was on the committee, was a French theorist called Poisson, Simeon Poisson. Very famous physics students will know about Poisson's equation. He did all kinds of important things in potential theory. But he was very much a theorist. He said life is good for only two things: discovering mathematics and teaching mathematics. That was his view. But one of the things that came up from the wave theory of light that Poisson noticed reading this, he realized that there was a sort of very strange consequence of this wave theory of light. The prediction was that if you had a circular disk and you fired a beam of light at it, then of course that would produce a circular shadow. But at the center of the circular shadow, the way the waves combine going around the outside of the circular disk, they would produce a bright dot on the axis. And that's clearly ridiculous. I mean, you must just get a black shadow. It's completely obvious. So Poisson said, look, this theory would give you this utterly ridiculous conclusion. Can't be right. Now, fortunately, one of the other members of the committee was Francois Arago. He was actually the chair of the committee, and he decided, he was experimentalist, so he decided to go and try it. So he set up this experiment, and he saw the spot. This is a modern version of it with a laser. There's a center, there's a bright dot at the center of the circular shadow. Rather unfairly, this is often now called Poisson's spot. I mean, Poisson did think of it, but he did it because he thought it was ridiculous. Arago demonstrated it, and it came from Fresnel's theory, so it should really be the Arago spot or the Fresnel spot, but it's called the Poisson spot most often. And over in Britain at the same time, or maybe even a little earlier, Thomas Young, absolute polymath, who did things like decode the Rosetta Stone and all kinds of interesting things in physics. But he did the famous two-slit experiment, where he showed that light underwent diffraction. And I'll say a little bit more about that in a moment, but this diffractive property of light, the fact that light was also a wave, changed everybody's view. So then the question is light a wave or is it a particle? And what implications does that have? Now, one crucial thing, we just need to get some sizes in our thoughts here. So this is a picture of a human hair. You have these on your head. I know it looks a bit like a tree trunk, but it's actually a human hair. And depending on whether you've got very fine hair or very wide hair or very thick hair, the thickness of the human hair goes somewhere between, I think I've got this on the next slide, somewhere between about 20 microns and maybe 200 microns if you've got really thick hair. But that's the typical thickness of a human hair, as shown here in a microscope picture. But light has a wavelength which is much, much smaller than the thickness of a human hair. So it's about 700 nanometers, 0.7 micrometers. So, and that's for red light, and it's even smaller for blue or violet light. So this is going to be a problem, because if light really is a wave, and it does seem to be a wave, that sets a fundamental limit on how good an optical microscope can be. Essentially, it's very hard to focus light below the optical wavelength. So optical microscopes, the kind of thing that Hooke started developing and people were then developing in the centuries afterwards, will never go essentially much below the wavelength of light. And what we now know is that atoms are of the order of a nanometer or less than a nanometer. So we're way out. So is there anything we can do? And the answer is yes, there is. We can use the diffractive property of light, but we need to use light with shorter wavelength. So probably the first people to really appreciate this, there's von Laue in Germany, but Bragg, father and son. So this is William Lawrence Bragg, the son, and William Henry Bragg, the father. And they decided to use light with a very, very short wavelength. They decided to use the newly discovered, at the turn of the 20th century, newly discovered X-rays. So around the time of the First World War, they were doing these experiments. Here is Father Bragg with his X-ray spectrometer, which you could hold in a hand, an X-ray source, a crystal in the center, and then you're essentially doing a diffraction experiment. So just to show you how a diffraction experiment works. So I've got a sample here, which is a CD of Palestrina, although any Renaissance polyphony will work. And I have here a light source. And what I'm going to do is just bounce the light source off the side of the CD. And what I hope you can see there are some spots. So sorry, it's probably going to be easier for the people on my right. I'll do it over here, and then maybe it's a little bit more noticeable there. So you can, I'm trying not to get any of the laser fired directly at you, but you can see those light spots. This is diffraction. if I do something with, let's see, have I got a, no, I've got a red laser pointer somewhere else, but if I did it with a red laser pointer, what you would see is the spots have a different separation because the wavelength is different. And this is essentially allowing me to measure the distances between the tracks on the CD. And it's a diffraction experiment, exactly the kind of thing that Lawrence Bragg did. We don't use this kind of experiment now. The sort of thing that we would use either is an X-ray kit here in the Clarendon laboratory, or you might use something like the diamond light source. So they've got bigger. I know phones have got smaller and chips have got smaller, but the X-ray sources have got bigger. So down the road in Oxfordshire here, the diamond light source is used for these sorts of experiments. We don't only use X-rays for doing this, but we also use neutrons. So just to give you an example of a modern diffraction pattern, so this is the same thing as the tracks on the CD. This is just some, I could have chosen one of thousands of examples, but this is just a very recent one. And the picture you can see in the middle here is a diffraction pattern. You can see the fits go through very well, and that allows us to deduce the crystal structure on the left. What you can even see here is volume as a function of temperature, so you can see actually the crystal expanding when you warm it up, because the lattice spacing between the atoms can be measured so precisely. Okay, well, I showed you a father and son, but here's another father and son. This is J.J. Thomson and his son, G.P. Thomson. And J.J. Thomson is the person who in the 1890s discovered the electron. And he showed essentially electrons are a particle. And his son, 25 years later, showed that electron is in fact a wave. Now this must have made Christmas lunchtime a difficult meal, but of course they were both right in the way that Newton and Hooke were both right. Light is both a particle and a wave. Electrons are both particles and a wave. It wasn't only G.P. Thomson who found that electron is a wave, but here's another couple. This is not father and son. This is Clinton Davison and Lester Germer, who were working in an American laboratory in New York. They also discovered this, and it was Clinton Davison who got the Nobel Prize, although sadly not Lester Germer. I don't quite know the history of this, but in all of these, there are a number of publicity photos like this, and all of them, Clinton Davison is holding the vacuum tube, and Lester Germer is always on the right, looking somewhat miserable. In fact, you can probably just about see in here on the right, Lester Germer is sitting next to a bucket of oily rags. So this is unfortunately sometimes the fate of the assistant. But they've done a very similar experiment to G.P. Thomson. And understanding what all of these people had discovered came to a number of people. Einstein was one, but another crucial person was Louis de Broglie. And de Broglie realized, as Einstein did, that there was this wave-particle duality. And in particular, he said that any particle with a momentum p is the mass times the velocity, is related to the wavelength by this relationship. H is the famous Planck constant. And if you put numbers into this, then what you find is that 300 kilovolt electrons have a wavelength of 2 picometers. And so that 2 picometers is much less than the size of an atom. So if you use very, very high energy electrons, you ought to be able to see atoms. So this was a brilliant idea. And so around 1930, the first electron microscope was built. This is a replica of what it looks like. And of course, with electron microscopes, you can get to even higher resolution than you can do with light. This is another one of these scary Hooke-type pictures. This time, I think of an ant blown up in an electron microscope picture. Of course, modern electron microscopes look rather more fancy, so they're all now computerized and look a lot better than they're used to. And I think it's appropriate at the moment, as we're in Oxford, just to remember Sir Peter Hirsch. He was a materials scientist, actually died just over a week ago at age 100. He'd been head of department in materials, I think, for about 25 years. So Andrew, our current head of department, that's a record you can beat. But what Peter Hirsch did was use a lot of electron microscopy. He developed the theory for understanding how electron microscope pictures can be used to understand defects and how the technique worked, and made very many pioneering contributions, even as you can see here, into his 90s. But there's a problem with an electron microscope. So with an ordinary optical microscope, we know what the components must be. They must be some kind of lens. You take the light in, you focus it. With an electron microscope, how do you focus electrons? You can't use a glass lens. So what can you do? Well, what you do is you use an electromagnetic lens. So this is something that provides a magnetic field, that provides curved field lines that the electrons can interact with. And the kind of way it works is a little bit more complicated than this. I tried to draw it. So this is how an electromagnetic lens works. The magnetic field produces a force on the electrons which is perpendicular. So they kind of spiral around the field lines. And so they focus like this. So this is the typical way that they work. But now we have a problem, because all lenses have an inbuilt disadvantage, and that inbuilt disadvantage is known as aberration. I've tried to give an example of it here. I made a really bad lens by taking a wine glass and filling it with water. Now, it does work as a magnifying glass, and you can see in the center of the image here, you've got a bit of my general relativity textbook magnified, but round the edge of the lens, it looks pretty awful. And this is the typical problem with lenses, that as you go further out, you get all these kinds of distortions. There are other types of distortion, but this is known as spherical aberration, or this wine glass isn't even spherical. So what can you do? Well, in fact, in many optical systems, and you have this in your fancy cameras, what you do is you put in a secondary lens. You put in a concave lens. And the concave lens corrects the aberration. If you get all the distances right, you can get the aberration in the concave lens to cancel out the effects from the convex lenses. And if you get the lenses in the right powers and distances, you can get something that still gives you the magnification you want. So the electron design, which I've drawn here, is what you want to put in an electron microscope. But there is a problem. And the problem is, because a magnetic lens works differently from an optical lens, turns out you can only make them convex. You can only make them the kinds of lenses that focus. You can't make diverging lenses. And this essentially comes from a fundamental result from Maxwell's equations of electromagnetism. And it was proved, I think, in about 1930 by Otto Scherzer. So he basically proved that if you have radially symmetric lenses, you can't have aberration correction because you can't have diverging lenses. And this was a huge problem for a long time, and it's limited the ability of electron microscopes to provide really sharp images to see atoms in the way that you would want them to. So how do you get out of this? Well, it turns out there are some clever strategies that have been employed. The first one was a bit of a trick. I mention this just for anyone who's the same vintage as me, because I remember when I did A-level physics, this kind of picture was on the cover of a physics book, because it was, this is the way you can see atoms. So there was this clever technique called the field ion microscope. Essentially what you do is you have polarized rare gas atoms on a tip, and you can image the tip, and by them bouncing off, and they fire off in particular directions onto a phosphor screen, and you get pictures that look a little bit like this. So this is a platinum tip. So I remember when I was at school, we were shown this picture, and yeah, you can see atoms, and you can, but it doesn't really look like an atomic surface, because you're seeing the atoms all firing off the tip in funny directions, so it's hugely distorted. So we really need something better. And something better came from this result from quantum mechanics. When you have particles going into a barrier in quantum mechanics, if the barrier is too high, classically the particles should just bounce off. But quantum mechanically, they can tunnel through the barrier and emerge the other side. Now, this is often talked about as a quantum mechanical effect, but the early 20th century scientists knew very well this is basic 19th century wave physics. It's not quantum mechanical, in a sense. The only bit of quantum is that particles are behaving like waves. This is something that was known about in light, because after all, if you, one famous phenomenon that you probably are familiar with is total internal reflection. Let's just get my brighter laser. That might show it up a bit better. So I'm just going to bounce a light beam off the inside surface here. Now you can see on there, the light, even though I'm shining the light up there, because I'm bouncing off the surface of this light beam, you can see that there's a, or maybe I get it on the floor, there you can see the reflected beam, and that's total internal reflection. The light can't go from the water-air interface, it's hit an infinite barrier. But if I had another bit of water just a short distance away, I would get tunneling. And I'm afraid I haven't set up this experiment, but it will work. And this can be shown in 19th century wave physics. So tunneling is a property of waves. Quantum mechanics just happens to say that particles like electrons behave like waves. But that means you should be able to see tunneling. And that led to the development in the 1980s of the scanning tunneling microscope. And the idea is very beautiful. What you do is you take a tip, a sharp, pointy tip, and you scan it across the surface. And you have electrons that go from the pointy tip into the surface. And you measure that current. And as you scan the tip across the surface, you started to be able to see these really rather beautiful images. And you're now not limited by any problems in optics or diffraction. You are now just limited by how sharp you can make that tip and what kind of information you can get out of the tunneling current. So this then leads to these beautiful pictures. This is graphite. You can see the hexagons on the graphite surface. This is actually an image from Oxford Instruments, who would like to sell you a scanning tunneling microscope. Here's another research image. This is molybdenum sulfide. And here again, you can see now atoms. And you can also see defects which are on the surface. But these now, you're looking at individual atomic elements. But there's more you can do, because what you can, what has been shown, particularly by Seamus and other colleagues in this room, is that you can get all kinds of information if you don't just look at the amount of tunneling current, but you look at its energy and voltage dependence and analyze that tunneling current in a great deal of detail. So the kind of idea here is that if you can measure the conductance, these are all images where you're scanning the tip over a surface, and if you can do this as a function of voltage and you can analyze this kind of information, then you can see these pictures emerge. You can take their Fourier transform, which is essentially their diffraction pattern, which is really emphasizing the fact that you've got some six-fold symmetry in these pictures. You can see these 6 dots, but you can also see this circle getting bigger, which is telling you about the way this energy, this is essentially, for the students here, this is energy is kinetic energy, which goes like a half mv squared. So this is a parabola. This is essentially a half mv squared behavior. So getting this kind of quasi-particle interference imaging has been absolutely crucial. We had an example in the conference today where this image was shown by one of our colleagues here. This is strontium ruthenate. And I'm really just showing this quasi-particle interference just to show the amazing resolution that is possible imaging these structures which exist in the strontium ruthenate. And you can really see them here. You can also see the effects of local defects. But there's more that you can do. So your tip that you scan across the surface, what happens if you make it superconducting? Now, the really key idea there is that then you're going to be introducing something that is really quantum mechanical. I mean, one of my hobby horses is that quantum mechanical tunneling is just wave physics. It's not really quantum mechanical. But superposition, Schrödinger's cat, which is both alive and dead, is one of the really key ideas in quantum mechanics. And we have that in superconductivity because we have states which are both empty and filled. And that's the key idea behind the superconducting ground state. So what happens if you made your superconducting tip, if you made your tip superconducting? Well, then what you could do is you could particularly pick up information about the superconducting order parameter as a function of position. And that's what you can get in these beautiful images, which Seamus's group has revealed so beautifully. What you're seeing here is not just the structure of the surface. You're seeing information about the Cooper pairs that make up the superconductivity. On the left, you're seeing the real space image. On the right, you're seeing its Fourier transform. So you're essentially seeing frequency dependence. And I can't also help but show this rather amazing image, which blends together what you see from just measuring the information on the topography, the shape of the surface, to then getting information about what the Cooper pairs are doing in the Cooper pair density. So enormous amounts of information is being revealed on the nature of superconductivity from these measurements. I've just got a few more images to show you and then I'm done. This is actually some more traditional electron microscopy imaging. This is in a material that we've been working on in my group in collaboration with some colleagues in inorganic chemistry. And again, what I think is so remarkable about this, and this is work from Hardeman, but you can see these incredible pictures of the perovskite layers, and you really are seeing the structure here. What you also notice is there are some defects, and so you can see some regions where actually the way the layers stack is slightly different, and this is all beautifully revealed in these images. But maybe finally, just to say that this aberration problem that I talked about, the fact that we were bedeviled by aberration, even that has been solved in some rather beautiful ways. What was realized was that theorem from 1930 that said that you can't correct aberration, you can't make diverging lenses. It had an assumption in it, as theorems always do, and that assumption was that you had rotational symmetry. So some people asked, what happens if we abandon that? If we get rid of the rotational symmetry, use a much more complicated magnetic lens? It's actually an optical, is one of the methods that's used. You get something that really distorts the image out of all bends it and stretches it in particular directions. But then if you have a compensating lens, you can put it back, and you can get something that is net diverging. So now, in the last, I think, sort of 10, 15 years, the development of aberration correction electron microscopes have really helped. What's also helped is the ability to layer up images and do a thing called tychography, which I'm not going to go into, that allows you to get these absolutely stunning images of atoms on surfaces. I think these are some of the most high-resolution pictures that you can get. Here's one final example on twisted bilayer tungsten selenide. Again, I'm really just showing this as eye candy because you can see the phenomenal beauty of this world. This is a world that's been opened up, first of all, by Hooke, I think. I think that manifesto that he articulated about the importance of observation is really the thing that has convinced probably most people that atoms do exist. The point is now you can see them. You can study their structure. You can find out all kinds of things on that nanoscale. And it's opened up an entire new world. I think in the same way that Hooke inspired Jonathan Swift to then have that imaginative exploration of these different sizes, we're now taking that even further. Exploring the nano world is now something that has opened up, and all kinds of exciting experiments are now possible. Thank you very much.